Right, so we are ready for the last talk of the day by Hoon Lee. But before that, I want to remind you, please, if you have a question, you are encouraged to have questions and to ask questions during the talk, fine. But please raise your hand so that you can be recorded, because otherwise this is lost, and then the speaker is answering an imaginary question. So please, so let's have Hoon Lee.
So yeah, thanks a lot to the organizers for the invitation and for bringing us together. Today I'll be talking about polar states in AdS3 holography, and it'll be based on first part will be based on a paper that came out in last November, and some in progress. These works were also the background for these works were motivated by previous works in the last couple of years. So the D1, D5 system in the large N limit provides a well-studied realization of AdS3 CFT2 holography. And specifically, the statement is that type 2B strings on AdS5 times S5, AdS3 cross S3 cross M4 with Q1, Q5 units of Riemann flux is dual to a CFT whose moduli space contains the theory of the symmetric orbifold, where N is equal to Q1 times Q5, plus 1 if you're considering K3, where M4 here, I'll be considering N equals to 4, 4 SCFTs in 2 dimensions. So the M4 of the symmetric orbifold will be T4 or K3. So at large N, the BPS spectra, or for the case of quarter BPS states, the elliptic genera on both sides agree beautifully. So for example, the chiral primaries in the symmetric orbifold of K3 and bulk Kaluza-Klein states in AdS3 cross S3 cross K3 share this large N spectrum. And these KK states are harmonic forms on K3 with degeneracies which are given by the Hodge diamond. Okay. And further decomposition on S3 and multiparticling gives the KK spectra. So this chiral primary sector is especially clean. But what about at finite N? Our bulk understanding here is very poor, to say the least. And we can even illustrate our lack of understanding at the level of the simplest sector in AdS3 CFT2, which is at the level of chiral primary states. So what do I mean by chiral primary states? The left and right moving chiral primary states of our symmetric orbifold theory, where we take NS boundary conditions around the spatial circle, are states whose dimension and R charges are related in this manner. So L equals to J on both sides. The partition function over the Hilbert space, HCC, of left-right moving chiral primary states will define in this way as a projection of the full NS partition function to satisfy the condition L equals to J on both sides. And so a non-trivial property at finite N is that any 2, 2 SCFT with central charge C has a finite number of such states. So the superconformal algebra implies that there is an absolute cutoff, which is at N on the dimensions and charges of chiral primary states. So HCC, the Hilbert space of chiral primaries, is a finite dimensional Hilbert space at finite N. And this fact is called the string exclusion principle. So the expectation from the boundary that the actual Hilbert space of the true Hilbert space of chiral primaries is finite dimensional. This expectation is called the string exclusion principle. Explicitly, the large N spectrum ZKK, which we can write with some simplification, is given by this set of numbers, which contain the degeneracies of these KK states. But there are only a finite number of chiral primary states in the finite N theory. So these are the values of, this is a palindromic polynomial, sequence of palindromic polynomials keeping track of the actual number of chiral primary states at given values of N. And I've colored in some parts of this spectra in blue and red because they deserve attention. So blue denotes the energies up to which the KK spectrum, ZKK, reproduces Zn. Okay, so KK spectrum will be useful for telling you what the degeneracies of your finite N theory is up to this cutoff colored in blue. And that's proportional, that bound is at n over 2. And red denotes so-called small black hole states at the center of the palindrome at energy, the total energy equal to n. Okay. So why are they called small black hole states? The cosmic censorship bound for charged black holes in AdS3, so I've written down this in terms of NS sector charges, is given by this inequality. And for chiral primary states, it turns out that this black hole bound can be satisfied only if you have h equals to j equals to n over 2, at which point the bound is saturated. And so if you include the right movers, these states have energy equal to n, which are the quantum numbers of these red states. Okay, so the red coefficients are small chiral primary black hole degeneracies at finite n. And the important for us for this talk is the states that lie below the black hole bound, which are called polar states. So why they're important will be explained in a moment. The chiral primary spectrum, the summary is that the chiral primary spectrum organizes into these 3 regions, which is the blue region described by the Kaluza-Klein states, the red region, the red, this diagonal, which are accounting for the degeneracies of these small black holes whose degeneracies scale like e to the square root of n. But there are these black wedges which grow infinitely big of polar chiral primary states which are explained neither by KK states nor black holes. So the question is, what bulk contribution do we need to consider to account for these polar part of the spectrum? I mean this as not as some asymptotic counting statement, but I'm asking whether there is a way to compute these interdegeneracies directly at, you pick a given value of n, is there some bulk way to compute these? So this puzzle at finite n is actually even more stark for the case of the elliptic genus of the symmetric orbit field of K3, which is defined in this way as a trace over the Riemann Hilbert space. Namely, what's important is that you don't have you project onto the Riemann ground states on the right. So you don't have a dependence on, you're not keeping track of the right moving R charge. The latter statement was not a result of the former, sorry. So I should say that, so you project onto the right moving ground states and you don't keep track of the right moving charge. So this is a protected quantity which counts quarter BPS states. So why are polar states important? The states below the black hole bound. The degeneracies of these polar states below the black hole threshold are precisely the input for constructing the full finite N elliptic genus via modular completion. That formula goes by the name of the fairy tale in this context. So if you just take the full set of modular images of these polar degeneracies, using the boundary theory degeneracies at finite n as an input, then you actually end up getting the full elliptic genus at that value of n as a convergent expansion. So this itself is not convergent, but the microcanonical version of this is convergent. So although the polar degeneracies are an input for constructing all the states above the black hole threshold, on or above the black hole threshold, we lack a bulk recipe for computing the polar degeneracies at finite n. So just to explain what this plot is, this was the NS sector black hole parabola. When we were enumerating the states in the chiral primary sector, we were focusing along this diagonal black line. This up to this blue of this diagonal is where KK states explain the spectrum. That's of order n over 2. This wedge is not explained by KK nor black holes. That was identified to be a quote unquote small black hole. And we also do not know the physical interpretation of the states as an exact statement in n beyond that small black hole point. Okay. So the goal of this talk is to propose a bulk description for the polar state degeneracies at finite n. And we'll proceed in 2 stages of increasing complexity. We'll describe the half BPS, this prescription for the half BPS chiral primaries of the symmetric orbifold of T4 and of K3. This is a simpler case. And then we'll describe this a richer case, which is a generalization of the idea of this one, but whose saddle structure is nevertheless very rich. So it involves a sum over more general orbifold backgrounds.
You will not be discussing the states above the black hole threshold?
So in this talk, I will not address the states above the black hole threshold. The so-called fairy tale expansion gives you a tool to, once you have the degeneracies of polar states as an input, it allows you to construct the degeneracies of every state on or above the black hole threshold. Yes?
Are those states with charges larger than 3 half n, are they not same as the ones with charge smaller than half n?
Oh, that's right. So you can fix those degeneracies. So beyond that red point, you can fix the degeneracies of those states using symmetry arguments. Okay. That doesn't tell you what states those are.
Okay. So the point is the most important point is the ones between 1/2 n and n, right? Is it?
But I would say because your spectrum gets cut off beyond order n in HH bar, JJ bar, I would say that wedge is also very. I'd say that's equally important as this wedge between the blue and the red.
Thank you.
Could you remind me where the bound on the Kaluza-Klein modes came from?
That was obtained sort of experimentally by Jan de Boer in '98. So there was this. So this blue was the bound bound of de Boer. He computed the Kaluza-Klein spectrum and the actual elliptic genus spectrum to certain values to large enough n. They have some polynomial. The coefficients have the polynomial independence, but with some extra inputs with some extra, some exclusion. You have to posit some exclusion principle assumptions, but in the end, what he gets is that KK spectrum agrees with the actual spectrum up to this level.
Well, maybe I'm remembering incorrectly, but at least for the half BPS chiral primaries, I thought that the whole black line between the origin and the red dot, it was given by Kaluza-Klein modes.
No, it's not. No.
Yeah. And then I'm remembering incorrectly.
Yeah. So if you impose this so-called exclusion principle, which is not the string exclusion principle that I talked about before, but sort of a exclusion principle that you apply by hand, introduced by Jan de Boer, then you can reproduce those degeneracies.
Not do Jan de Boer. Let's just analyze what states we get from gravity, right?
So those the partition function of those states. So the elliptic genus actually is divergent if you don't apply this exclusion principle. But for the chiral primary states, which are non-divergent, they explain the spectrum up to this point. This wedge is not explained by KK.
Well, the reason I'm asking is because I vaguely remember this paper we wrote with Maos and Lunin, where we looked at the 1/2 BPS. This must not be exactly what you're talking about.
So
the 1/2 BPS.
These are 1/2 BPS states.
Yeah, so the 1/2 BPS, my memory was that they were all Kaluza-Klein modes. But maybe my memory.
Yeah, so as far as my understanding goes, one cannot reproduce at finite n the degeneracies within this wedge. I'd be happy to learn about your work.
So these two wedges, are they related by the spectral flow, or?
Which wedges? This one and that one? Or?
I mean, the left and right
Oh,
wedges.
this one and that one. Yes. They're related by spectral flow.
Okay, thank you.
Okay. So here's a bulk proposal. Here's a bulk proposal for chiral primaries. So the proposal is that the finite n spectrum of chiral primaries and the symmetric orbifold of M4 is given exactly by in terms of this formula. The right-hand side is the bulk. So these z hat k's are one-loop half BPS partition functions of type 2B theory on AdS3 cross S3 mod zk cross M4 and spectral flows thereof. So the spectrum, we'll explain these points, but we'll denote the spectral flows in this formula by mu that preserve NS and S boundary conditions. Okay. So this formula also captures the nonpolar integer genericity corresponding to the small black hole at any integer n. Being a one-loop half BPS partition function, the right-hand side depends very trivially on n, whereas the left-hand side depends quite sensitively on n. So why does the sum truncate to a finite polynomial, to just state the results? The one-loop determinants, which are contained in the z hats on AdS3 cross S3 mod zk, contain bosonic negative modes in the zk twisted sector that one can work out, and these produce alternating signs in front of these partition functions. Some analog of this phenomenon in AdS5 was worked out in these papers previously in the context of giant gravitons. These negative modes also happen to introduce one-loop corrections to ground state energies / charges. So the infinite sum over saddles, because of these alternating sign cancellations, collapses to finite n polynomials. So the interpretation of that would be that non-perturbably, we seem to find vastly fewer number of quantum states than any classical analysis around a single background would suggest. So computing the one-loop partition function around any background will give you an infinite number of states. It seems that only through these vast cancellations between these one-loop partition functions that you get your sum truncates to a polynomial. So we think that this provides a bulk explanation of the string exclusion principle. So how do we arrive at this? The key observation that'll be useful for the rest of this talk is that the one-loop partition functions, z hat k in the bulk, that sum up to the finite and answer, are encoded in the analytic data of this grand canonical partition function. So a notion, it's this A averaging over n. But its analytic structure is very rich and contains a lot of bulk physics. So contains the data of partition functions of bulk saddles. Let's review how to construct this grand canonical object and then show how to extract the sum over geometries from it. So in symmetric overfolds, there's a universal way to construct the grand canonical partition function, curly z. So you start with the partition function of a C theory on M4 in the Riemann sector. The so-called DMVV formula provides a recipe for constructing the grand canonical partition function. So the grand canonical partition function is constructed exactly using the coefficients of the C theory as an input. Well, we're interested in chiral primary states in the NS sector because the NS ground state is dual to the AdS3 cross S3 cross M4 background. Upon spectral flow and restricting to this chiral primary sector, you get this grand canonical partition function. It's very simple, comparatively simple. So for the symmetric overfold of K3, the grand canonical half BPS partition function can be written exactly in terms of the Hodge numbers of K3, because those count the Riemann ground states. And a well-appreciated fact is that the large N KK spectrum can be extracted from this curly Z by taking the residue at the pole closest to the origin on the p-plane. And here, this pole is actually at p equals to 1, coming from the small n equals to 1 term of that denominator. So yeah. So, but we can ask why should we stop there? We can ask whether a bulk interpretation exists for the other residues that may contribute to the inverse Laplace transform for p. I have a question mark here because this equality is not true. Why? Because of its singularity structure. Let's enumerate all singularities of this infinite product on the p-plane. So the grand canonical partition function has 4 infinite towers of these simple poles, which I've labeled in this way. These towers of simple poles just differ by some signs in the exponent. They arrange into kth roots of unity on the complex p-plane, where m labels the root of unity, and k is some discrete label for these poles. So these are simple poles. But there is also an impenetrable wall of essential singularities at this radius. So if you were to look at the Riemann sector, they're like 1 over eta function singularities at every root of unity. But so it's clear from the singularity structure that the standard residue theorem doesn't apply. But it turns out that a variant of the residue formula holds for curly Z. So the essential singularities turn out they do affect the degeneracy growth of the residue at any simple pole, but indirectly. they turn out not to contribute explicitly to the sum over residues. So for now, let's concentrate on understanding, so taking these lessons of this key observation of the analytic structure of the grand canonical partition function having to do with bulk saddles. Let's first focus on understanding the bulk interpretation of the residues at the individual poles of this grand canonical object. So let's start at the simplest, with the simplest case where k equals to 1. So this is the bottom of these 4 towers. What are the bulk interpretations of the bottommost components of these towers of simple poles of the grand canonical partition function? The residue at the first pole corresponds to the KK spectrum of AdS3 cross S3 cross K3, as we stated before. And it can be found that the residues at the other 3 poles are related to the large N KK spectrum in this way. Okay? So they have the same structure as the KK spectrum, but with some minor modifications. So what are their bulk interpretations? The space-time n equals to 2, 2 superconformal algebra admits a symmetry under an operation called the spectral flow, which is a family of automorphisms labeled by the parameters eta and eta bar. The spectral flow operation acts on, by eta, acts on the generators in the left moving sector in this way, and similarly on the right. So if you spectrally flow by an even unit, it preserves the fermion boundary conditions around the spatial circle, while flow by an odd unit will change the fermion boundary conditions. Okay, so this spectral flow operation that's defined for superconformal algebras is realized in asymptotically AdS3 spacetimes by large gauge transformations of gauge fields that change their asymptotic values by a constant eta and eta bar. So these A and A bar are SU2 cross SU2 left cross SU2 right gauge fields in the supergroup Chern-Simons gravity on AdS3 that you get from KK reducing 60 sugra on AdS3 cross S3. And there's a Lorentzian way to calculate the charge measured at the asymptotic spatial boundary. It's given by this integral. And it's related to the left-moving R charge of the dual CFT in this way, which is proportional to C. So we see that if we spectrally flow the gauge fields A and A bar by units, say 2, 0, 0, 2, and 2, 2, which all preserve fermion boundary conditions. So if we flow global AdS by these values, that they would induce the overall charges, which are given below, for the flowed AdS3 solutions. They correspond to the weights that the extra weights that you saw in these k equals to 1 residues. We also need to explain why the KK spectrum on the flowed AdS3 backgrounds have flipped R charge signs relative to that on unflowed AdS3. So we can recall that we're interested in the contribution from the bulk path integral to this quantity, which is defined as a projection of the full partition function to the chiral primary limit. So our bulk saddles, our bulk sum over saddles should sum over configurations that preserve fermion boundary conditions, as well as the chiral primary condition, where the projection onto the Hilbert space of chiral primary states is implemented by taking Q and Q bar to 0. So we should sum over AdS3 cross S3 cross K3 backgrounds that are spectrally flowed by even integers, as long as they survive the projection. So we know the Hilbert space of chiral primary KK states. So suppose we're tracing over that. And suppose we flow our AdS3 background by these units, which preserve fermion boundary conditions. This would transform the weights of the KK states counted in the partition function. This actually turns out to result in an important sign change here, where minus has changed to a plus. So one can work this out directly from the spectral flow rule that I quoted here. The projection Q and Q bar to 0 of the flowed background now enforces the anti-chiral primary condition on the left and the chiral primary condition on the right, where these conditions are now expressed in terms of the flow generators. So if we now take the trace over the original space of KK states after flowing by to 0, this is what we find. So that explains this minus exponent of the y's and y bars. So it turns out that only flows of AdS3 cross S3 cross K3 by these units turn out to survive the projection onto chiral primary states. Okay, so we'll identify the residues 0, 0, 2, 0, 0, 2, 2, 2 at the 4 bottommost poles of this grand canonical partition function in the half BPS sector, with the KK spectra of spectrally flowed AdS3 cross S3 cross K3s. So, but we still have left the 4 infinite towers of simple poles at higher K on top of these spectrally flowed backgrounds. The sum over residues restricting to the unflowed sector for now, with fixed K, so summing over M, which labeled the roots of unity, gives this residue. We claim that this is the one-loop half BPS partition function of the type 2B theory on AdS3 cross S3 mod ZK cross M4 background, which is defined by this metric with these identifications. So actually what one has to do is take this global metric with these partial identifications and sort of unravel it to make it an AdS3, asymptotically AdS3 cross S3 geometry, and we'll do that. So the simultaneous ZK orbifold of AdS3 cross S3 preserves the chiral primary supersymmetries. So because the supersymmetry condition is L equals to J, the ZK orbifold needs to act both on AdS3 and S3. So before moving on, let's note some features of this spectrum. The one-loop determinants around the AdS3 cross S3 mod ZK backgrounds contain fractional powers of y and y bar in units of units of 1 over 2k. So what that means from the bulk point of view is that states obtained by quantizing the fluctuations of these orbifold backgrounds have R charges that are quantized in fractional units. But the sum over M projects the spectrum onto half integer J and J bar. So we'll work this out from the bulk point of view. The classical weights for the R charge of these orbifold geometries, they have an accumulation point as k goes to infinity. And that normally would be problematic for the convergence of the sum over saddles. But what saves the day from these accumulation points, in this case in particular, is that the one-loop determinants contain bosonic negative modes in the twisted sector of the theory. So the effect of these negative modes is to shift the ground state charge from the classical value, which was given by this, to this quantum corrected value, which resolves the accumulation point as you fix n and take k equals to infinity. So these negative modes in the ZK twisted sector has an even more important consequence, which is that these orbifold geometries labeled by higher k contribute to the full partition function with alternating overall signs. In the gravitational path integral, we expect these signs to rise from Wick rotating the path integral contours for an even number of bosonic negative modes on these orbifold backgrounds. So we will find these negative modes in the twisted sector from a worldsheet treatment, but we believe that in a space-time path integral, the contours for these negative modes need to be rotated, and that's what produces these signs. So let's now reproduce our residue by computing the one-loop partition function on these orbifold backgrounds. So the classical computation proceeds as follows. The charges J and J bar of an asymptotically AdS3 solution are computed from these SU2 cross SU2 gauge fields A and A bar of Chern-Simons supergravity that descend from the reduction on S3 of AdS3 cross S3. For these ZK orbifold geometries, the metric on S3 becomes non-trivial when we undo the ZK identifications here to actually turn this global solution into a conical defect metric. So because there is non-trivial mixing between the AdS3 and S3 coordinates, that results in a non-trivial gauge field profile in conical AdS3 with these NS sector charges, which you saw in the weights of the classical weights of those of the residues interpreted as a one-loop partition function. And that explains the n-dependent prefactor seen in these residues. This is really the only n-dependence, apart from a phase. This is the only n-dependence in these one-loop partition functions. The one-loop computation proceeds as follows. To compute the one-loop spectrum, we'll borrow tools from worldsheet results of a paper in 23 by Gabriel Guo-Motor. They computed the tensionless ring spectrum on these orbifold backgrounds in the hybrid formalism based on the current algebra PSU 11/2 at level 1. So before ZK orbifolding, in the treatment by Eberhard, Gabriel, Gopakumar, the partition function of the worldsheet theory is given by a sum over worldsheet spectrally flowed sectors. So this was worked out. So the fact that you have to sum over worldsheet spectrally flowed sectors was worked out in a beautiful paper by Maldacena and Oguri. So it turns out that in this hybrid formalism, one has to sum over these worldsheet spectrally flowed sectors from 1 to infinity. The spectrum of these ZK orbifold backgrounds can be found by considering a ZK orbifold of the worldsheet theory, which is generated by the worldsheet action expressed in terms of, which in order to not introduce extra notation, I've just expressed the worldsheet charges in terms of the space-time charges. There's a simple relation between the two. So G is the worldsheet generator of ZK. The result is that on AdS3 cross S3 mod ZK orbifolds, the worldsheet spectral flow W simply gets quantized in units of 1 over K. So that's what Gabriel Guo-Motor found recently. Since the partition function of the worldsheet theory on AdS3 cross S3 cross T4 specialized to the chiral primary sector, it is given in this way. It follows that the chiral primary partition function of the worldsheet theory of this orbifolded background must be this formula where W is replaced by a 1 over K quantized value. So the worldsheet spectral flows are fractionally quantized. And here you see the negative modes already. the negative modes, which are denoted by negative powers of y, and y bar, are present for small n going from 1 to k minus 1. If you multi-particle the single-strength spectrum on these overfold backgrounds, it recovers precisely the one-loop part of the residue that I've showed before, up to the important phases, which I'll comment in a moment. So this is the main part of the anticipated residue. From the worldsheet perspective, this object is a perfectly valid partition function that's invariant under the worldsheet zk overfold projection, which is written in this way, in this standard way. So namely, G acts trivially on chiral primary states, as you can see from the action of the action of G. So both this and that so the exponents will evaluate to 1. So they, if we restrict to chiral primary states, they actually, they're already invariant under this zk overfold projection, so you don't have to do anything else. And this is a well-defined one-loop partition function. But our residue actually has some extra phases. It suggests that we need to further project the fractionally charged spectrum onto the zk invariant subsector with half-integer charges. Because if you take just one of these, you'll get a fractionally charged spectrum. So you have a zk action omega, which I'll write as omega, which enforces Gauss's law on R charges. This zk action omega enforcing Gauss's law on the R charges is actually different from the zk action G used to define the worldsheet CFT on AdS3 cross S3 mod zk. So while G acts trivially on all chiral primary excitations of this orbifold background, the zk action omega, which is different from G, which you can read off from the residue, on the space-time spectrum, acts non-trivially only on states with fractional R charges. So we thus find that the insertion of this projection operator with respect to this omega corresponds to an extra zk projection that's not required in the worldsheet treatment of overfolds, but is nevertheless required in the holographic computation of the BPS partition function at finite n, once you sum these contributions up. So a question which is natural to ask, but has not been, has appeared in some parts of the literature, but hasn't appeared clearly in this very context, is whether this Gauss's law projection admits a gravitational origin interpretation as a zk family of these orbifold saddles. That's a path integral way in which something like this Gauss law projection could arise. So assuming that this projection with respect to omega is part of the prescription, we can reproduce this the z hat k's, which were interpreted as one loop half BPS partition functions on AdS3 cross S3 mod zk, via the trace over the perturbative BPS Hilbert space on this background. Well, the other residues turn out to be BPS partition functions on so-called asymmetric zk orbifolds, where this zk are allowed to act separately on the left and the right in a way that's consistent with these labels. We identify them with spectrally flowed zk orbifold backgrounds. Okay, so it's finally time to ask whether Zn receives contributions from all four towers of the zk orbifolds that we considered so far. But this is not quite true. So due to the wall of essential singularities, only the poles inside the wall turn out to contribute. Actually, that's a strange statement because it would normally be a strange statement, but it turns out that the poles beyond the wall have one-loop determinants with infinitely many negative powers of y and y bar, which regularize to a vanishing answer for, say, y and y bar less than 1. So that's one reason why these backgrounds don't contribute. Some other backgrounds might not contribute while some backgrounds do. So the contributing set of saddles depends on the fugacity space region under consideration, which is a Stokes phenomenon.
Sorry, may I ask a question
Yes.
about this pole discussion?
Yes.
So the original definition, I mean, originally you start with a small contour around p equal to 0, right?
Yes.
A tiny contour.
Yes.
And now what you're trying to do is make it into a very big contour that goes to infinity.
Yes.
Is that?
Yes. Yeah, but you can't because there's a wall of essential singularities. So
Right,
you
right.
can't assume you can't apply the Cauchy, the residue theorem, but one can regularize this the infinite product and consider a sequence of residues as you remove the cutoff on this infinite product. And you can quantify the residues coming from the essential singularities as well as the contributions from the residues outside the wall of essential singularities. And it turns out that these contributions vanish as you take the cutoff to infinity. Only the contributions, only the residues from poles inside the wall of essential singularities turn out to be finite. But the set of poles which are inside the wall of essential singularities can vary as y and y bar vary. Okay, so here's the proposal for the chiral primary case. So let's let this S, y and y bar, which depends on y and y bar, denote a subset of the 4 infinite sequences of poles that lie inside the wall of essential singularities of the grand canonical chiral primary partition function on the p-plane for given values of the complex fugacities y and y bar. We propose that this formula holds, which is the formula that I showed earlier on. That is only the residues from poles located inside the wall of essential singularities of the grand canonical partition function contribute to the finite n BPS partition function. The bulk interpretation of the discontinuous change of the summand is that the supersymmetric partition function Zn of the type 2B theory on asymptotically AdS3 cross S3 cross M4 backgrounds contain different Stokes sectors in which different infinite subset of the spectrally flowed AdS3 cross S3 mod ZK saddles contribute to the path integral. So the structure of this sum over saddles changes discontinuously in the space of these fugacities. So for example, the x-axis here denotes the norm of y, and the y-axis denotes norm of y bar. So suppose that y and y bar are both smaller than 1. We can actually take it to be bigger than 1 because we know that the full answer is polynomial in y and y bar. But suppose we take it to be both of them to be smaller than 1. It turns out that the 0, 0 saddle is 0, 0. So the non-spectrally flowed AdS3 cross S3 is the dominant saddle. But the structure of subleading saddles changes as you cross this dotted wall. The dotted wall is called a Stokes line, where you have an infinite tail of subleading saddles that change discontinuously as you cross some value of a parameter. So this is our proposal for the Stokes sector classification. Okay, so
Normally, when we talk about Stokes sector, there is some parameter that's becoming very large, right? There is some, let's say, function of C. Let's say there is C equal to 0 where the parameters of order 1, there is large C, and then there is a semi-classical approximation of Stokes sectors.
Yes. As you change the phase of
You change the phase.
Yeah.
Yeah. What is the phase that you're changing, and what's the parameters becoming large?
Yeah, the parameter that's relevant here is y and y bar, or the ratios thereof. So this is viewed as like a coupling of the problem. So here you're expanding in the region where you're expanding it, in when you extract the microcanonical coefficients, you're expanding in the series in y and y bar. Here you would be expanding in one where y and y bar, etc.
So the center of this diagram is the region where you can't apply anything.
Yeah,
and then
that's
the
right.
Stokes lines are in the periphery of this diagram. In all around.
So these are the Stokes lines, but yeah, that's the
center
general
doesn't mean
point.
anything.
Yes,
Okay.
I agree. Yeah.
Now I understand.
Also, like in the Stokes, like a Stokes phenomenon, because normally like a series is asymptotic. In Stokes phenomena, normally the series is asymptotic, but I thought like here, the series in Y's are not asymptotic.
That's right. Yeah, the series should be convergent, at least in a microcanonical sense.
But then you're saying that there are still some Stokes line and Stokes phenomena here.
Yes. In order to recover the same set of degeneracies, in this region of fugacities, you would need to sum over these sets of saddles, infinite sets of saddles. In this region, you would need to sum over these sets of infinite set of saddles.
I think he's claiming that these powers of Y he's summing is not conversion, right? It's an asymptotic series. Is that the claim?
No, so the powers of Y can be resummed into an infinite product formula, so it must be convergent. So
I don't see
each
how
of
they
these
can...
are an infinite product formula from the one-loop determinants. I mean,
I think I agree with Shota that in order to have the Stokes line, you need the series to be somewhat ill-defined, right? Otherwise, how can subleading term change?
maybe one can call this an analog of Stokes phenomenon, but one really does. You can check directly that the 0-2, the one-loop partition functions for the 0-2 saddles are not well-defined here. Okay, so actually they regularize to a vanishing answer, and the necessary and sufficient set of saddles turn out to be this, and that set changes drastically as you cross these dotted lines. So maybe you can call it an analog of Stokes phenomena.
I think if you consider the microcanonical, the coefficient of this expansion is conversion. But if you consider the entire series, I think it's not conversion.
I think it's unclear. Microcanonical, so this expansion gets you the correct microcanonical degeneracies for every microcanonical degeneracy. So if you're able to get all the correct coefficients of a convergent expansion in Y and Y bar, then I think to me that let me know if I'm wrong, if it doesn't converge in the canonical sense, but I would think that the series does converge canonically.
I think one thing you can do is you plug in some finite Y value, and then look at how the value change when you increase K, and to see whether that sum converge.
Yeah, so it is extremely oscillatory if you fix a finite Y and Y bar value. I'll show why it's oscillatory.
So then you can see how it grows. So I think that will grow. So it's not,
it will grow with very. It'll have a tail of high power Y and Y bar series. So that the large K z hats will contribute at higher powers of y and y bar. But with huge coefficients. So if you fix y and y bar, this sum will be extremely oscillatory. But we know that the microcanonical coefficients can be retrieved by a finite number of terms in this sum over z hats. Yeah. Let me know if I'm wrong, but for a convergent series, if you get all the microcanonical coefficients correctly, I think that means that the canonical sum formula would converge as well. Thanks for the questions. Okay, so let's conclude the discussion of these chiral primaries with the demonstration over the sum over saddles for this most quantum example. It even works at n equals to 1, where, as in the beginning of this talk, we set y equal to y bar for visualization purposes, but you can generalize, and assume that y is smaller than 1. You find that you're on this dotted line, and the surviving saddles are simply given by the 0, 0 zk hats. Okay. So our expectation from the K3 sigma model is just counting the Betty numbers of K3. So starting with the k equals to 1 term, which was the KK spectrum, as you add more and more terms in the sum, you get this for the k equals to 1 term. This, as you add the k equals to 2 term, but now you notice that there are drastic shifts, changes in the signs of the contributions of these saddles. K equals to 3, k equals to 4, 5, 6, up to 9. And one can argue that this keeps going on. You have a propagating tail of zeros as you add more and more terms. And so at any given microcanonical degeneracy, by summing over these alternating sums of one-loop partition functions of these zk orbifold backgrounds, you do retrieve the correct spectrum at n equals to 1. And that's by summing over stuff that's almost independent of n. So it depends very trivially on n. And you can do this for different values of n, et cetera. Okay. So far we've described the bulk prescription for the half-Bpez chiral primary degeneracies at finite n. What's the lesson? The grand canonical partition function seems to provide an organizing principle for the geometries that sum up to the finite n answer. And it's natural to ask whether we can generalize this to, first, the polar states of the elliptic genus below the black hole threshold. One can also ask this question for those above the black hole threshold. So as a review, the elliptic genus counts these quarter BPS states unrefined by the right-moving R charge. The DMVV formula gives the grand canonical partition function, so grand canonical elliptic genus, which is expressed as a sum over n weighted with p to the n. This function is a well-studied so-called Siegel modular form, which is a generalization of the usual modular form applicable for SL2Z. And we'll denote the chemical potentials for the P, Q, and Y as sigma, tau, and Z. Okay. So the analytic properties of these phi 10s are well known. So again, as a review, the polar states are those with that sit below this parabola, but above the black line, where this is drawn in the NS sector. So they're important because they're the input for constructing the full elliptic genus via modular completion. But it's not known how to compute the finite n polar spectrum in the AdS3 via AdS3 bulk methods in general. And we'd like to have a bulk prescription for these degeneracies. So applying the lessons that we learned from the chiral primary case, we're led to study the pole structure of inverse phi 10 as a function of P. So all the non-trivial poles of the grand canonical elliptic genus in the grand canonical fugacity P are inherited from this inverse phi 10 function. The analytic the properties of this function actually have been studied extensively in the context of BPS Dion partition functions of heterotic strings on T6. And the poles of this function are classified into linear poles, which happen to be double poles, and so-called quadratic poles, which will not concern ourselves for this talk. The linear poles determine the polar data entirely. The linear poles in P, one can write this in this way. So as a function of sigma, it takes this simple form. As a function of, in the P plane, it again has this root of unity type structure, where these exponents are subject to some non-trivial conditions, which we'll explain physically shortly. So these linear poles are actually double poles on the P plane. That's a bit problematic. So this is due to the fact that elliptic genus is blind to the right-moving R charge. So if you had introduced a fugacity for the right-moving R charge, it would resolve these double poles into simple poles. But because you don't have this J bar for the elliptic genus, you get double poles, unlike in the case of chiral primaries. But we learned from chiral primaries that individual geometries are associated with simple poles on the P plane. So this is sort of problematic if one is interested in just generalizing the lessons from the chiral primary case. So to extract individual geometries corresponding to the simple poles, we'll consider a slightly regularized version of the problem by considering the so-called Hodge elliptic genus. So this is the quarter BPS partition function with the y bar included. This is not protected, but it's protected in the limit, in the elliptic genus limit, where you take y bar to 1. So the idea for introducing this object is purely for regularization. You could have worked alternatively with the full partition function in the zero momentum and winding sector, the full grand canonical partition function. The additional fugacity y bar for the right moving R charge resolves each double poles into a pair of simple poles, which we label by S bar equals to plus minus 1. So these actually will correspond to right moving spectral flow parameters. So it's important that this quantity is not protected, but we'll discuss combinations of one loop quarter BPS partition functions on pairs of quarter BPS backgrounds that we believe are well defined and protected when we sum them up and take the elliptic genus limit. So that's like putting the residues at two simple poles together. You have divergence from each of the residues, but the divergences cancel out and you get a finite piece. So here's a proposal for polar states. The polar part of the NS elliptic genus at finite n is given by this sum over geometries. So this is actually a microcanonical statement, because we're trying to describe polar states which are described microcanonically. So these Z hat S bar are the one loop quarter BPS partition functions on asymmetric AdS3 cross S3 mod ZK cross K3 orbifold backgrounds where the ZK action is generated by this G in terms of the space-time charges. So they could act separately on the left and the right via these SNS bar parameters. But they're subject to consistency conditions. Yes. Okay, thank you. So the sum runs over geometries labeled by these conditions. They're arising from the constraints on the linear poles, but they have a physical interpretation. So they correspond to physical consistency condition of these backgrounds as we now explain. So these backgrounds are defined by global AdS3 cross S3 with ZK identifications, where these are the S dependencies. The parameters S and S bar control how the overfold acts on the left and right SU2 factors of S3. And these are the classical energies and charges of these solutions in the NS sector. Okay, so, but the NS Hodge-elliptic genus projects you, it's defined as a projection onto the right moving chiral primary states that have L bar equal to J bar. If you look at these conditions, if you look at the charges, you can easily find out that the asymmetric overfolds have satisfied this condition on the right only if S bar is plus or minus 1. So that you can just read off from these formulas. So for each choice of K and S, this yields actually two geometries labeled by plus minus 1 on the right with these classical weights. And these geometries are related by a right moving spectral flow. The interpretation of S as a left moving spectral flow parameter, so one can come to that interpretation by noticing that these S and S bar dependencies are precisely the spectral flows. Also restricts S to odd values because you're going from an R sector to various NS sectors. So the classical actions of these pairs of geometries related by right moving spectral flow become degenerate in the elliptic genus limit. In fact, the 1-loop quarter BPS partition functions of the individual geometries above blow up as you take the elliptic genus limit due to the 1-loop determinant. But you find, however, that the elliptic genus limit of the combined pair of the 1-loop quarter BPS partition functions is finite and protected. So as an example, something I mentioned earlier was that when matching the large N elliptic genera of a symmetric overfold of K3 and the KK spectrum of type 2B on AdS3 cross S3 cross K3, you encounter a curious puzzle. Namely, it's that the large N elliptic genus of the symmetric overfold has Fourier coefficients that depend non-trivially on N, while the Kaluza-Klein spectrum on a single AdS3 cross S3 cross K3 should not depend on N. And it does not depend on N. But a somewhat ad hoc way in which the match was restored in the literature, in the early literature, was by positing an exclusion principle for the KK spectrum, which makes the KK spectrum on a single AdS3 cross S3 cross K3 background explicitly N-dependent. But our considerations suggest that in the bulk, one actually needs to account for the KK spectra of not only the vacuum AdS3 cross S3 cross K3, but also its pair related by two units of right moving spectral flow. So you actually need to sum over two stuff whose classical actions are indistinguishable. So while each of these things depend trivially on N, the combination, because you cancel the divergent part and the finite part involves derivatives. Involves derivatives. The combination has a non-trivial independence, and it recovers precisely the large N elliptic genus of the symmetric overfold of K3. So this non-trivial independence arises more generally as you sum up the twofold degenerate set of these orbifold geometries. So so maybe I'll skip this part. This is just a comment on the worldsheet part of the calculation and an explicit formula for these z hats. But maybe one important thing to note is that the invariance of the one-loop spectrum under modular T for the orbifold imposes a level matching condition for the asymmetric orbifolds. The energy is on the left and the right. So this gives you precisely the constraint that you had from the mathematical linear pole classification. Okay, so to final, this is the final main slide. You get quite a rich microcanonical bulk phases of these polar states, which are, they are these wedges under the red, but above the on or above the black. Here I've only denoted the dominant AdS3 cross S3 cross K3 geometries in each polar wedge. But more generally, at a given charge, there's a rich but a finite set of subleading orbifold geometries that you can work out that contribute in addition to the dominant one. So as a summary, we gave a holographic prescription for the chiral primary partition function at finite n, and extended some of these lessons to the more richer quarter BPS polar states, whose data is sufficient to recover the entire elliptic genus. But precisely how that modular completion works out and the physical interpretation of this modular completion involving these ZK orbifolds is unknown, and that would be very interesting. It would be very interesting to have it would be quite illuminating to have a gravitational path integral derivation for these results, and it'd be nice to if there are more general lessons from this top-down setting to AdS3 quantum gravity. So with that, that's the end of my talk. Thank you.
Questions for Ji-hoon, or more questions, should I say?
So I have some basic question about this ZK orbifold. So this ZK orbifold also acts non-trivially on the boundary of AdS, right? So
that's right. So you take global AdS3, the ZK orbifold acts non-trivially, but when you actually compute the contribution of these ZK orbifolds, you actually have to go to the base space, where you take one of the wedges and you make it, you sort of you extend that to actually make it asymptotically AdS3.
Okay, so that's what you actually.
That's what you actually need to do. Yeah.
Okay, but then there is still some non-trivial action on the S3 part, like R symmetry part, right? Or
that's right. Yes. When you do this unraveling to the base space, the S3 components of the metric mix with the AdS3 components, and that's what gives you, upon KK reduction, gives you the non-trivial gauge field profiles.
Does it have a boundary interpretation of this this weird thing that you need to do on S3?
There are some proposals discussing, yeah, I think it's quite convincing. So the boundary duals of the ZK orbifold states are, so the NS sector vacuum is given by, the NS sector vacuum is given by a product of one cycles. There are n of them, right? It's been proposed in the literature that that the dual states of these AdS3 cross S3 mod ZK geometries are the states where you have n over k of these k cycles, where these k cycles are BPS, they're once created by acting with BPS twist operators.
So
the question for the Hodge elliptic genus, from the bulk point of view, each AdS3 orbital fold, I mean, the claim would be that you have to add these two AdS3 orbital folds and then take y bar goes to 1 to get something finite. But I know that you list this here as that's not gravitational path integral, but I mean, I think if you're claiming that you have to sum up two geometries, that is a sort of path integral argument, and each geometry does not have the correct boundary conditions to be the elliptic genus, to contribute to the elliptic genus. So are you sure this is really the right prescription? Like maybe at the level of formulas it makes sense, but individual terms are not BPS basically. Or
there may be a better way to think about it.
Okay.
Like there may be simple attempts don't work, but there may be some BPS preserving regularization of this quantity that doesn't involve y bar.
Yeah, we'll talk later.
I think that's what you're looking for.
Yeah, that's what I'm looking for. Yeah. Okay.
But naive attempts don't seem to work.
How naive are we talking?
Pretty naive. So anything that distinguishes these two saddles must naively be involve J bar. But as soon as you introduce J bar, you're not. That's not protected.
Well, you know what I'm going to say. We'll talk later.
Okay.
Can you also consider orbifolding black holes in AdS3 times S3? Can you put the black holes in your orbifolds geometry?
Yeah. So if you take the spectrum of polar states at a given value of n that you got from these one-loop partition functions of these orbifold backgrounds, and then you do modular completion of those degeneracies, you will get the full set of microcanonical degeneracies of the elliptic genus at any finite value of n.
Yeah. Okay. I understand. Thank you.
But yeah, actually studying that would be very interesting. How that works would be very interesting.
Thank you.
Maybe following up with Matt Heidemann questions. For example, Turiachi and Iliesu considered these black holes with, near extremal black holes, which have finite temperature but angular momentum and so on. So that can one do something like that in AdS3? I mean, the naive thing would be try to do the same thing in AdS3 and find smooth solutions that would contribute to this index. Because
so
the elliptic genus.
You mean beyond the polar states or for the polar states?
Well, naively, the index is related to the entropy of rotating BPS black holes, right?
Yes. Yeah.
So one would wonder whether their story here would give some geometries which are smooth and contribute to the index.
Just a comment. We did it in. We did it for the BTC black hole with charge. In that case, yes, you can find smooth geometries that.
I think it can be done in this
but
case
not
as well.
Yeah, for this.
I think it can be done.
Okay.
I'll make a comment.
One would be asking about the leading and then subleading contributions to this.
Yeah, we didn't look at subleading, just the leading BTC. I was just saying that in principle the method works the same.
Okay. You have a problem constructing some solution that has those boundary conditions, right? The y bar independence and q bar independence, that's part of the problem, right? If you want a SUSY solution, that's part of it.
Yeah, that seems to be the problem.
Maybe here you want to have solutions that always have the interpretation of the trace, right?
That's right, yeah.
You wouldn't accept the solution which is like a modular transformation of black hole.
At least for polar states, we wouldn't expect.
Okay.
Yeah, S transform to be relevant.
That's I think the difference.
right. So I see no further questions. It looks we arrive at the end of the first day of the conference. So we'll reconvene tomorrow at 9 a.m. Thank you.